All right, so let's go ahead and begin today. So first of all, you might have noticed the door has been fixed. And there's a lock with a code. And this is the code right here. It's the same as last quarter. So some of you were in my 133 last quarter, and we were in this one. And I gave you a code and it's the same. So if you ever want to get into the room, as long as the building is open, you can get into the building and you'll be able to get into the room. Might be handy, especially towards the end of the class, if you don't have a Basis 3 board. When you get to the point where you actually download the Otter onto the Basis 3, it could help having that code. Okay, so today is the reg file that you're going to build the reg file, which is part of the Otter hardware. It's actually hardware assignment number 3. So after the lecture, which is probably going to be about an hour or so, you'll have enough information where you can do that assignment. Okay. So before we talk about the reg file, I talked a little bit about it, but we'll talk about it in more detail. But before we do, I want to go over some of the things we've already talked about, like the program counter and also the memory module. Okay, so most of what I talk about with the program counter and the memory module is reviewed. There'll be a few new things that I haven't talked about with those. And then when we get to the reg file, it's mostly going to be all new stuff. Okay. So first, let's talk about the program counter, because you built this last week. And remember, you modeled this in Verilog or System Verilog last Tuesday. And it has a register part. And it's called a counter because it will increment by 4 if you're doing the program in sequence. Also, with the addition of this bus, it allows jumps and branches. Okay. So the first question I have for you is, when you modeled this in Verilog and you built it, what did you make that reset? Is it active low or active high? Everybody remembers? It's active high. All the enables and like reset, they're all active high for Otter. I don't think any of the enables or anything, right reads, what have you, I don't think any of them are active low. They're all active high. So yeah, you made this active high. Now, what does reset mean again? Okay, what does clear the registers mean?
Set the value is 0, restore value.
Yeah, 0. Yeah, when we clear or reset, no matter what it is, you're making the contents 0. So when this reset is active high, and what kind of reset is this? Is this asynchronous or synchronous? Synchronous, right? Because you put it in and always have that block, right? So yeah, this reset is active high synchronous. So at the time of that 0 to 1 transition of the clock, provided this is high, the program counter is going to be reset and its output is going to go to 0. And what is the purpose of the program counter? Like, why is it in this order? What is it providing us? Like at the output, what does it provide?
It keeps track of the address of next instruction in the board.
Right. Exactly. Okay. Provides address. Instruction to the executed. So when this program counter gets reset, its output goes to 0. That means now it's addressing the instruction at register 0. Okay, and that's always true that the first instruction be executed at address 0. Okay, that's where your program always starts. Now, I put a Otter diagram on each bench. Where does this reset come from? What module provides the reset? Right, control unit FSM. If you all designed FSM finite state machines in 133, and when you design an FSM, where do you always start? What diagram do you always start with? State diagram. Right, a state diagram. So when we get to the point where you're ready to build that control unit, you're going to draw the state diagram. And it's actually not a very complicated state diagram. There's not that many states, actually. But one of those states is called the initial state. And in that initial state, that's where reset gets put the value 1. Okay, so when the Otter initializes, the output of this program counter is going to go to 0, and we're going to be at the instruction of that address 0. And that's the first instruction of any program. Okay. Okay, how about this PC write? Did you make that active low or active high? Which one? Active high, yeah. Like I said earlier, I don't think there is any active lows for these. So that was active high. That's also synchronous. So when this PC write is 1 active, and we get that 0 to 1 transition of the clock, what's going to happen? You designed it, so you simmed it.
It's gonna output these specified input from the box.
Yeah, exactly. Right. When PC write is 1, at the time of that 0 to 1 transition of the clock, whatever this input is coming from the MUX, it's going to get written into the register. Now it's going to be at output. Okay. And as we talked about, this MUX has these different inputs. Here is the instruction that's 4 addresses away from the instruction that was previously executed. Here is an offset to an address that causes a jump. Here's an offset to an address that causes a branch. Here's an address to an offset that causes another jump. Then these other 2 inputs have to do with interrupts, which we probably won't even get to this quarter because we lost some time with those 2 classes that we lost to a holiday in the storm. Okay. But what determines what this MUX outputs?
This is source.
Yeah, PC source, because that's what goes to the select line. So if PC source is a 0, it's going to connect the previous address plus 4 to the output of MUX. If PC source is 1, then it's going to be this address that's offset by whatever JALR provides in that command, the immediate, and so on. So where is PC source? Like, where is PC source coming from? On your diagram, the Otter diagram. What is that? Control, right, control unit decoder. Right, so this is also coming from the control unit. Now, it's a different part of the control unit because the control unit is split up into 2. It's split up into an FSM and a decoder. And if you were to look at all the outputs of the control unit FSM, there's all like reads and writes, different kinds of reads and writes mostly. And then if you look at the outputs of the control unit decoder, it's all outputs that go to the MUXes, right? There's like 5 or 6 MUXes in that Otter. And all the selects of the MUXes go to the output of the decoder. So that's why we call that part of the Otter control unit, because through the reads and the writes and through the select line of the MUXes, that hardware is controlling how the data flows through the rest of the Otter, the rest of the hardware. Okay? Now, this input here, this JALR, this input branch, and this input JAL. And we learned about branches last class. Right? Branches is how you can go through the program non-sequentially. And remember that branch instruction had an immediate value. And that immediate value acts as an offset to the present instruction address that you have. With jumps, it's the same idea. Jump commands also have an immediate value that acts as an offset to the address that you're currently at. Okay, jump is just an unconditional branch. Okay. Well, those offsets come from this hardware called a branch address generator. Okay, we're gonna learn about this next. We're gonna build it next. Okay, but I just wanted to point out, where these inputs of the must that go to the program counter come from. Okay, so the output of this program counter that has the address of the instruction to be executed, it goes to this input of the memory module. Okay, this address 1 input. Okay, so the next thing we're going to talk about is this memory module. But before I do, any questions on the program counter? Everybody have a rough idea how it's working, providing the address in the next instruction you executed? Right, we get these writes and reset coming from the control FSM. We get this piece of source coming from the control decoder. What this mux is doing is choosing from these 5 inputs. See, that's going to determine whether, the output of this mux, and therefore the value of the piece of source is going to determine whether we go through the program sequentially, if it chooses this mux input, or whether we're going to jump or branch. Okay. All right, so let's move on to the memory module. Now, you can see I use different colors here for the inputs and outputs. What I mean by what you see in pink is we're not ready to talk about those yet. Okay, so this address 2 input, D2, this D out 2 output, these 2 inputs, and also these 2 here. Okay, we'll talk about those later. Okay, I'm just going to talk about what's in the black right now. And I already talked a little bit about what address 1, read enable 1, and also D out 2 are, but let's go over that again. So this program output connects to this address 1 input. So now you're going to have the address of the instruction to be executed here at this input of the memory module. And in order to get that instruction that's at this address to the output of this memory module, you have to do 2 things. You have to make this read enable 1 equal to a 1 because it's active high. And also this read enable is synchronous. So if this read enable 1 is active high, by the way, that comes from the control unit FSM. At the time of the 0 to 1 transition of the clock, the contents of this address, namely the instruction at this address, is now going to be here at D out 2. So this is where your machine code instruction is going to be. Okay. Right, so to go to another instruction in your program, first this memory address would have to change in the program counter, and then you have to have another clock pulse while this is active at 1. Right? And you go to the next instruction. All right. And as we're going to talk about, this instruction connects to the reg file. It also connects to something called the immediate generator. Okay, so we're going to talk about that next week also. Okay, but you'll see what effect connecting this output where the instruction is to the reg file has today coming up. Okay, but before we move on, there's 2 other inputs I want to talk about here. There's this input size and input sign. And then what this notation means, this IR, is that means instruction. So this is telling us bits 13 and 12 of the instruction, machine code instruction, is going to this input size. And bit 14 of the machine code instruction is going to this input sign. So let's look at our instruction manual, right? That has all the details of every instruction, including the machine code for that instruction. So I'm going to go to the instructions for load and store. Right? Remember we have LB for load byte, LBU, load byte unsigned, load half word, LH, load half word unsigned, load word. And I talked about this last class, at least I think I did. Why is there no load word unsigned? We have load byte unsigned, load half word unsigned, along with load byte, load half word, but we only have load word. There's no load word unsigned.
Because the most significant bit is used to tell what the sign is, so the word in there is like cause an error.
You're kind of close. I mean, you're right. The most significant bit is always the sign bit, but you know, the 32 bit also has its most significant bit is the sign, just like the byte and half word byte.
When you have a forward, it doesn't have to sign extend. So
Yeah, that's the key thing is, see with load byte, where it's treating the data as signed, if you look at the description, it will sign extend. Right? And remember what sign extend means is it takes the most significant bit, which is the sign bit, and just takes that value and extends it out to however many bits. Like 32 in this case. And same with the half bit. But a word is already 32 bits. So you're never going to sign extended. And then where the sign bit comes in is that, well, if it's a signed number, you're going to do sign extension, like we just said. If it's an unsigned number, we just add with zeros, right? Because with an unsigned number, regardless of what the most significant bit is, because it's not the signed bit, you're just going to put zeros in front of that value to keep it the same. Okay, so this 14th bit here is telling the memory module whether we have a signed case or an unsigned case. You know, if you look at load word, if you look at the 14th bit, it's 0. If you look at load half word, the 14th bit is 0. If you look at load byte, the 14th bit is 0. So you see 0 means signed in this case. If you look at load bit unsigned, the 14th bit is a 1. If you look at load half word unsigned, the 14th bit is a 1. So 1 here means signed. Okay. Now these two bits, the sides, well, byte, half word, there's a word, there's also store byte, store half word, store word. Well, if you look at these two bits, or excuse me, these two bits, 12 and 13, if you look for load byte, those two bits are both 0. And that's true for load byte unsigned or just load byte. Load half word, we have 0, 1. Same thing for load half word unsigned. Load word, 1, 0. So you see, this tells the memory module whether you're dealing with a byte, a half word, or word, either doing a load or a store. Okay, so I wanted to take this time to point this out because again, the software and the hardware, they're interconnected. Can't understand what's going on with the hardware without understanding the instructions. You can't understand the instruction unless you know what's going on with the hardware. Okay, so the good news to all this is that this module you're given, Dr. Hummel designed. And you're not going to need it today, but when you need it, won't be for a while. We're going to give it to you. Okay? And sign extension happens here. So you don't have to worry about, you know, designing something that does sign extension because the memory module will do. Okay. Okay. Another thing that we talked about is how the Otter memory is organized. So how many bit words do we have? There's 32 bits, right? It's organized as 32 bits. Right, so remember, we made this diagram where, each row is 32 bits. And then how is it addressed? Yeah, it's byte addressable, right? Which means every byte has an address. Byte addressable. So how many byte addresses do we have in one word? Four, right? It's 32 bits, right, divided by, okay. So yeah, got all these bytes here, each byte has an address. I'm not gonna write out all the zeros in front, but remember we had this drawn. Oops, made a mistake. Start with two. One, two, and this is that, three, then four, right? We talked about how all the word addresses are created by four, right? Again, that's the reason for that +4 there when you go through the program sequentially. Okay, so everybody sound familiar? We spent some time on this, right? Okay, now how about there's also segments, right? This Otter memory is segmented. Do you remember the names of the segments? Do you remember what we call the segment that has the instructions? Not the data, it's actually below the data.
Oh,
No,
it's not.
No, that's something. What is it?
It's the code segment.
Right, code segment. Yeah, the code segment is where the instructions are. Then the data is above that. Okay, we haven't talked a whole lot about what goes in there, but we will. Not today, but later. And then you have something called a stack, okay, which also we'll talk about later. That kind of ties into subroutines. And then, MMIO, memory mapped IO is up here. Okay, what's significant about memory mapped IO? Exactly, right, that. All our motor fields, right, whether it's input or output, the CPU knows it by an address. Okay. Now, there was a name. Now, the other thing too is remember, each row here has a 32-bit address, right? So this address is all zeros. It goes up to all Fs, right? 8 Fs. And then from address 0, all zeros. Yeah, I'm not writing all the zeros here. Up to 0, 0, 0, 0, F, F, F. Okay, so this address range that contains the code segment where the instructions are, the data segment, and also the stack segment, we call that a certain name. What do we call that? Something memory. Real memory. Right, that's real memory. The reason we call it real memory is the address range of real memory is set by hardware. It's set by the FPGA on the basis board. So the programmer, the designer, has no control of that other than using a different developmental board. If you're going to use the basis 3 board, you're stuck with this address range. Okay. Now the ranges of the segments within real memory, right? The range of code, the range of data, the range of stack, that's set by the program. Okay, and if you look, the code section goes up to address 00055 F, F, F. And we talked about how, that 64K bytes, divide that by 4. That means you can store in the code segment 16K instructions. Okay, and Dr. Hummel or one of the other doctors that developed this, that school decided, well, 16K is plenty for our needs. You're not going to come anywhere close to that many instructions. Okay, thank you. Okay. But those can be easily changed. By the end of the course, you'll see how those address ranges for the code segment, the data segment, and the stack segment are set. Okay. It's too early for that now, but by the end of the quarter, you'll see where that's determined, but it's easily changed by the program. Okay, again, real memory address range, you can't change without getting a different FPGA. Okay, let's see. So I think that's all I wanted to talk about with them. Do you have any questions up to this point? Again, this is mostly review. Or should be. All right, well, let's move on now to mostly new stuff. And that's looking at this RAID file. So here are inputs and outputs. We only have two outputs. Okay, RS1 and RS2, those are outputs. Everything else are inputs. So this is WD for write data, EN for enable, ADR1 for address 1, ADR2 for address 2, and WA is write address. And then, of course, we hit the clock. So again, we got a sequential circuit. Okay. Now notice. Okay, so the output of the memory module, where the instruction to be executed is, goes to the write file. It also goes to immediate generator, but like I said, we'll talk about that next. Right now, we're just looking at what goes over to the write file. So what this notation means, just like it did over here, it just means the bits that are connecting to that particular input. Right? So just like there's two bits connecting the side, right? The 13th and the 12th, and there's only one bit, the 14th of the instruction that's attached to the sign there. Here, we got bits 19 through 15 of the machine code of the instruction going to address 1. We got these 5 bits, 24 to 20 going to address 2, and we got these 5 bits, 11 to 7 going to the right address. Well, take any instruction that has registers in it. Like, for example, I took this instruction here, the add instruction, okay, where we're going to add these two, the contents of these two registers, register 10 and 20, and put the results in register 5. Well, if you look at the instruction, again, if you go to the instruction manual, there's just a wealth of information in this instruction. You should get very familiar with it. All right, if you look at this instruction, when you write it in assembly code, you put add, and then you put a register here, which is going to be the destination register. RD stands for destination register. That's where the result is going to go. And you have RS1, okay, that's a source register, where the contents of that is going to get added to the contents of this other source register, RS2. And then if you look at the machine code, this is the machine code for that instruction, right? So this right here. Well, 24 to 20, these 5 bits right here, that's the address for RS1. Okay, and then 19 to 15, so these 5 bits, that's the address for RS2. And then bits 11 to 7, those 5 bits, that's the address for the destination register. Okay. Now, how about these 7 bits here? Bits 0 through 7, those 7 bits. What do those 7 bits represent? You had to know that for the first hardware assignment when you did the reverse engineering. Like, what are those 7 bits called? That's the octet. Okay, the rest of the bits for this particular instruction are just filler. Okay, but you know, here's bits 12 through 14 again. So, you know, if that was a load instruction or a store instruction, well, they would have meaning. Okay, but for an add instruction, they're just filler. Okay, so how does this reg file work? Well, first of all, the reg file has what we call dual asynchronous reads. And it has a single synchronous write. Now, what's the difference between synchronous and asynchronous again? Right, synchronous depends either on a rising edge of a clock or a falling edge of a clock, correct. How about asynchronous? Doesn't depend on the clock, okay? That's the first case in this class of having something asynchronous in the otter, right? Everything so far, like when you did the program counter, both the reset and the PC write were synchronous. And here the write is synchronous, but the reads, both reads are asynchronous. Okay, so let's see how this works. Well, if I want to write to this, and remember, write is putting data into a register. Okay, a read is getting data from a register. Well, if I want to write to the reg file, this enable has to be a 1. Also, because it's synchronous, it needs an edge of a clock. And remember, the otter, everything's rising edge. Okay, so all the synchronous components we have in the otter, they're all rising edge. So what will happen when this enables a 1 at the time of this 0 to 1 transition to the clock is that whatever data we have here on this input, WD, it will get written into the register whose address is here. Right? So, like in this example, our address for the register we're going to write to is 5. So whatever data is here, and it's a 32-bit, we look at the otter, it's 32 bits. Okay, well, that 32 bits is going to be written into that 32-bit register whose address is right here, these 5 bits in the machine code. Okay. Now, if this enable is not a 1, if it's a 0, then it's reading. It's doing asynchronous reading. Okay. See, this is different than the memory module, right? Because the memory module, at least for these 2 inputs here, see how you have a read enable 2 and a write enable 2? You have a separate read and write here. Okay, here you just got 1 enable. If it's a 1, you're writing. If it's a 0, you're reading. And again, if you're reading, you don't care about the clock. And when a read happens, the contents of this address is going to be here at this output. And the contents of this address is going to be at this output. And they're going to be there simultaneously. Okay, that's what we mean by a dual async read. Okay? All right. The next thing to talk about is how the reg file memory is organized, right? This is how the otter memory is organized, and that's in here, right? Remember we talked about that. All of this is inside our memory module, okay? Now we're talking about the reg file, so we're talking about something different. Okay, well, the memory inside the reg file, well, I should ask you, because we talked about this, and there's also a handout on everyone's bench. That's the same handout that I gave on the first day that shows the reg files and the names. How many reg files are there? How many registers are in this reg file? 32, exactly. So you see there's 32 rows, and I can keep going. Okay, here's a key difference. See, there's a key difference between how the reg file memory is organized and how the otter memory that's in the memory module is organized. Remember, this memory is byte addressable, right? Each byte has an address. The reg file is not byte addressable. Okay, only the 32 bits have an address. And it starts at address 0 and it goes up to 31. That's why you see on the handout that the names, right, X0, X1, all the way to X31. So, you know, register 0 has address 0, register 20 has address 20, register 31 has address 31. And how many address bits does it take to represent 32 different things, right? 0 to 31, it takes how many bits? 5. So that's why there's 5 bits here, there's 5 bits here, there's 5 bits there. Okay, does that make sense? Okay, so we're at the point now where we can talk about how to do this or how to model the reg file in Verilog. At least I think anyway. I talked about right enable, talked about yeah, so we're ready. But before I go into how you're going to model this in System Verilog and basically outline hardware assignment number 3, do you have any questions up to this point?
So on the reg file, when it reads, it outputs what's in the register. When it writes, it changes what's in the registers.
Correct. Right. When you're writing, you're putting data into a register. When you're reading, you're just looking at the data that's there. Yeah. Okay. So in System Verilog, the way you're gonna model this reg file is you're gonna use an array of vectors. And I think the easiest way to see this is just through an example. So let's say we wanted to create 7 10-bit vectors. And you see each vector would be equivalent to a register. Well, this is the code. It's just a single line. In fact, remember for hardware 1, when you learned how to make a mem file, then you learned how to put the mem file into Vivado, and then you simulated to see how it progressed through that program, looking at the instructions in hex, right? There was that hex listing, then you saw it on the timing diagram. And there you used the prog-rom that Dr. Hummel designed. And in the video, remember I had a video, I explained a little bit of the code of Dr. Hummel's code. And one of the lines was this, because this same line is used in the prog-rom. It's also using an array of vectors for that memory. So what this will create, and you see, you just start with logic, and then before the word RAM, you have these numbers here you see in brackets, and then after you also see numbers in brackets. Well, what this will create is an array that looks like this. It's going to have 7 rows, 0 through 6, basically 7 registers. 1, 2, 3, 4, 5, 6, 7. The bottom one here in the picture would be address 0. The top one here would be address 6. And then it's going to have 10 squares that represent the bits. So 2, 4, 6, 8, 10. The most significant bit is what you put here. Okay, so the most significant bit would be 9, and the least significant would be 0. By convention, we call the 0th bit the least significant bit, and the highest is the most significant bit. I mean, you could do this the other way, flip these, but it would be, not conventional. The only person I've seen do that is Dr. Mealy does that for some reason in a couple of his modules that I use in 33, but everywhere else it's done this way. Okay, so that's how you're going to create the registers. It's through this array in Verilog or System Verilog. Now, once you have the array created, if you have this here, RAM, and then in bracket a number, this takes the 10-bit data at register 0. If you have this, right, bracket 4, bracket 7, this takes bit 7 of the register at address 4. Okay, this here takes bits 4 through 7 from register 3, address 3. And then if you do this, if you put like a variable within the brackets, that's gonna take the 10-bit data at this address, whatever this address is. Okay, so this is just, instead of using a number, you're using a variable. And instead of using like 0 like we did here, we're using a variable. Okay, that works the same way. Now I gotta move the camera. I remembered. I'm 2 for 2 today. I remembered in my earlier section too, so I think that's the first time that's happened. Never remembered 2 sections in a row, so it's a good day. All right, so on that handout with, the registers for the reg file, remember I mentioned how the first 5 X0 through X4, they're specialty registers. What's special about register 0, X0? Right, what's special is that register always has 0 content, right? It's hardwired to 0. Well, that just doesn't happen by itself. You got to make it happen. Okay, so that's one of the key things today for hardware assignment number 3 and for designing this reg file is you have to make the contents of register 0 always 0. Okay, now there's basically 2 ways you can do it. You can see I like one of those. I like this way of doing it. Initialize everything to 0, right? Initialize the contents of the register to 0, and then never write to it, right? You make the contents of register 0 to begin with, then you never write to it. Well, it will never change. It'll just stay 0 all the time. That's one way to do it. Another way to do it is just make it 0 every time you go to read from it. Okay, like make it 0 before you read from it, but do it at that time. Okay, so there's 2 ways to do it. This is an or here. All right, but like I have written here, I like this. I like just initialize it to 0 and just never write. That's just the way I prefer. So if you decide to do it this way, where you initialize the contents to 0, well, here's the code that's going to initialize the contents of all the registers to 0. Okay, it's just using a for loop. So you can use this code if you want to do it this way. Okay, I'm providing that for you. Now, as we said earlier, these reads are asynchronous. They don't depend on a clock. Now, there's various ways that you can model asynchronous inputs in Verilog. In fact, if you're in my 133 section, and I'm pretty sure most of the 133 instructors teach it, where you can make something asynchronous within an always FF block. You have like your positive clock edge, and you could have like a positive read edge. Because whatever you put in the parentheses of that always FF block, it gets evaluated on the edge that you put there, right? So if you only put positive edge clock, it's only going to evaluate the block at the time of a transition of the clock, which makes it synchronous. But if you put some other, if you put like a positive edge read, well, then it gets evaluated on that positive edge read that isn't dependent on the clock, and that makes it asynchronous. So, I mean, that is a way that you could do it. But I find this easier. Okay, another way that you can do asynchronous reads is just use an assign statement. Assign statements are just going to happen all the time. And you see here, as long as we're not writing, okay, as long as this is 0, we can just read for all of time. Okay, now the reason for that is you're going to see next week is that this data that we're reading here at the outputs, RS1 and RS2, they eventually go to the ALU and some other stuff in the Otter. Well, that circuitry that these 2 outputs connect to determine whether that data is going to be used at all. There's instances, or in fact, most of the time, you know, there'll be data here at these outputs. But we don't care. We don't care what the data is because it's not being used downstream, if you will. Okay? So you can just have an assign statement for each of our outputs. Like, for example, you know, if I call this RF underscore RS1, and again, RF is for reg file, right? So I'm being more descriptive than just putting RS1. It's good to put something in front of an output or input to know what module it pertains to, because at the end of the quarter, when you're trying to troubleshoot that, and you're looking at your SIM and you got like 50 signals on your SIM, it's nice to have, you know, some notation to know, well, that's the output of the reg file. You know, that's the input to the program counter, as opposed to, oh, what input is this? Oh, let me look at my diagram. You know, it saves you time if you make your inputs and output things descriptive. So anyway, what this assign will do is it will take the contents at this address and assign it here to this output, right? So that's what makes the read. See, it's taking the data at this address 1, and taking the data at this address 1 and putting it at this output. Okay? So that's an easy way, and in my opinion, it's the easiest way to do an asynchronous. Just use an assign statement. Okay? All right, so last thing here, oh, actually, I did better than an hour. It took me a little longer this morning, so maybe there's a few more questions. But this is the outline of what you have to do for hardware number 3. Okay, so first you're gonna have, like you do for all your modules, right? You're gonna have the module name, and then you gotta declare your inputs and outputs. Again, these are inputs, so you have, well, 6 inputs counting the clock. Right, 1, 2, 3, 4, 5, 6. You only have 2 outputs. Next thing, create the array. So you're just going to have a single line like this, right? But the numbers are different, right? Because you want 32 registers, and each register is 32 bits. Then if you're going to do this, right, the method I prefer, well, then you want to initialize your memory to 0. And I'm giving you the code. Okay, then the next thing that would come is your async reads, right? So you have 2 assigned statements. And then the last thing is doing the synchronous write, where you haven't always had that. And where did you most recently do a synchronous write? You just did it not too long ago, because where did you have to do it? Over here, right? This was a synchronous write. Okay. I think the challenging part of hardware 3, and I'm not going to tell you how to do this. You've got to figure out how to do it in Verilog. But this is really the only thing that's kind of new, is that you have to make sure that the contents of register 0 always remain 0. Okay, so, you know, no matter what you're doing over here with these inputs, you never have a case where the contents of register 0 become 0, because if that were to happen, if the contents of register 0 become something other than 0, your adder will never work. Because there are instructions where the instruction is counting on that register 0 has 0 contents. Yeah, question.
So for the first one, when you initialize it to 0 and never write to it, does that essentially rely on the programmer to not write to it?
Well, if you model this register 5 correctly, it won't matter what the program's doing or what the programmer is doing.
Oh,
It would be hardwired 0. Yeah. So the programmer wouldn't have control if it's hardwired 0. And that's exactly what you want. Because yeah, if you left it up to the programmer, they could, you know, make a mistake or more easily make a mistake. If you hardwire it, right, they can't make that mistake. Yeah. So this is really the part that might take a little bit of thought. Okay, everything else I'm kind of laying out and giving you most of it, and you know, you've done a synchronous write before. You know, just making sure this never happens. You may have to think about a little bit what you have to do in the code to make that happen. Okay, you know, my 8 to 11, a few people came up and, you know, they were kind of like showing me what they did and, you know, is this right? And I just said, sim it, find out. And, you know, I wasn't trying to be snide. I hope they didn't take it that way, but, you know, seriously, when I've written code, like when I was doing this, I thought it looked good. Then I simmed it and it wasn't right. So I had to go back and think about it some more and eventually I got it. But you know, that's what design is, right? It's an iterative process. You know, don't be afraid to try things. You're not going to break anything, you know? And, you know, I'm quite sure you'll find a more clever way than I did to do it. Okay, so anyway, at this point, you should be ready to go ahead and tackle this and do hardware assignment number 3. Blake should be here in about a half hour or so, but like always, I'm here to answer questions.
Quick question.
Sure.
I have a difficult time understanding what the thing is significant byte address for.